All right, good morning, everyone.
Good morning.
Any questions before we get started? We're okay? Okay, so today we're going to be covering quite a bit of stuff today, and it's gonna require that you really understand the geometry of what's going on here. So please, while I'm going through this, if you have any questions about anything, stop me. But then also at the same time, keep in mind that everything I write down, I'm going to send you a copy of my notes today. And then also you can always go back and watch the video. So be paying more attention to, comprehension of what I'm doing, as opposed to I better get this down on paper, because you can always go back and review that. So I wanted to start off by just reviewing quickly what we know so far, what we've explored. The first thing is that if we're given y as some function of x on some interval ab, that we can calculate the area under that. That's basically the fundamental theorem of calculus, and we just set up this integral, right? And then after that, last time we started talking, well, was it last time? Well, a little bit last time and the time before, we started talking about finding the area between two curves. And so then we had to talk about, okay, well, you can have functions of x or you can have functions of y. And depending on what you have, that will dictate which type of, which version of the formula you're going to use. So if we're trying to find the area between two curves, and our two curves are both functions of x, then what we do is we construct a bunch of vertical rectangles. We find a formula for each of the vertical rectangles within this region. And then once we find the formula, which in this case is the top curve minus the bottom curve, that's the height of the rectangle, and then times the width of the curve, which is dx, then we just integrate that from a to b. So a to b gives us our variation of x. And that's something that I haven't pointed out to you, but I'm going to point out for what we're going to be doing later, is that when we're talking about this rectangle, this arbitrary rectangle in here, remember that rectangle, it kind of like we start at the very left end at A, and the integral is adding them up as we move that rectangle across the region all the way until we get to B. And so if I were to pick some arbitrary rectangle, let's say that one right there, the position of that rectangle, in other words, the distance from the y-axis to that rectangle, is always going to be x. Okay, because x varies between a and b. That's what these limits of integration are telling us. It's like x is going to start at a, so we're going to start our rectangle at a. Okay, position-wise on the x-axis, that's the position. And then we will vary that x value all the way to b, so that will slide that rectangle across the region. Does that make sense? Okay, we'll need that later. Okay, then we said, all right, well, wait a minute. What if you don't have functions of x? What if you have functions of y? Well, then what we do is we turn our rectangles horizontally and we move them up and down, right? And that way we always have a right curve and a left curve. And so again, we figured out a formula for the area of one of those rectangles. It would be the right curve minus the left curve times dy this time, because we're moving up and down. It's the y value that's changing, right? Any questions on that? Okay, and then we start talking about revolving things around the x-axis, right? That's what we started, kind of ended with last time. And so the whole idea here was we take that same region, we take a rectangle, and then what I did is I drew it over here to the side, and I said, okay, the top of that rectangle will be the blue curve, the bottom of the rectangle will always be the red curve, no matter where that rectangle is, right? It'll always be this scenario. And so we use the formula for the volume of a washer in order to create a formula for the volume of one of those rectangles being wrapped around. And what we came up with was this idea of trying to determine the outer radius and the inner radius. And so the formula for it was pi. Pi came out, because pi could be inside, but it's constant, so I just pull it out. the outer radius squared minus the inner radius squared times dx. And that was the volume formula for a washer. And then again, we're going to slide the rectangle across the region, which basically creates a bunch of washers, and we're adding them all up. All right. So last time I didn't stress this, but I am going to now. When we talk about the outer radius, I want you to always think about the outer radius as being the distance from the axis of rotation to the outer edge of the rectangle. So in this picture, you know, the distance we're talking about is this distance here in green, because our axis of rotation, I labeled it right there with the little green arrows. The axis of rotation is the x-axis. So the distance from the axis of rotation to that outer edge is just the value of that blue function, right? It's just whatever whatever the blue function, I didn't name it, but if I call it the blue one f of x and the red one g of x, then that distance from here to here is just the value of f, right? That's all it is. And the radius on the inside is just the value of the g function. That's not going to be the case for the rest of the day. That's why we need to be clear that it's a visual thing. You're looking at a distance from the axis of rotation to that edge of that rectangle. All right. Okay. I thought we would just do an example to start, and then we'll get into the new stuff. All right. So it says here, sketch the region bounded by these two functions, and they're both functions of x because they're solved for y. That's a real clear indicator that you have functions of x. If both equations are solved for y, then they're going to be functions of x. If they're both solved for x, then they're functions of y. So that's just something to kind of keep your eyes open for. So we have these two functions of x, and we want to first find the area of the region using vertical rectangles. Then I'm going to force you to find the area using horizontal rectangles. And then I want to find the volume of the solid generated by rotating the region about the x-axis. So it's kind of like everything that we've just gone through. Let's just make sure we can do it all, and then we'll move on. So I'm going to start with the region itself. So the region looks like this. I have square root of x, which I need to know what that looks like. It looks like this. That's going to be my blue curve here. And then I'll use a different color. I'll use green. X minus 1 is just a line, right? It has a slope of 1, and it's been moved down 1. So let's say that's -1 there. I know my line goes and does something like this. Oh, you know what? Hold on a second. Hold on. That's not what I wanted. I messed up. Let's just, I don't have time to fix this too much. Let's just make the line x instead of x minus 1. There we go. I meant originally I was going to put square root of x minus 1, but I forgot to write it down, so I'm just going to leave it like this. I'm going to move that line up. That way we have a region, right? So here's our region. And what we would like to do is find the area of it using vertical rectangles first. So if you're using vertical rectangles, right? Vertical rectangles, then you know you have to use the formula that goes integral a to b, top minus bottom, dx, right? That's what we're going to use. So we need to figure out, do we know the top function? I think we do, right? It's obvious from the picture. The top function is the square root of x. The bottom function is just x. And the only thing left is to find the limits of integration. So what are we integrating from, right? And you can just see by looking, 0 is our first limit of integration. And the other one you would get by setting the two equal to one another, right? And solving. But just again, by inspection, just look, would you agree that x equals 1 is the solution, right? Just look, if you plug 1 into both those functions, you get 1. So we know that they hit at 1, 1. But again, you could solve that if you needed to, but I'm just gonna do it by inspection. So that's it. That is the integral. Now we would have to calculate that, right? We'd actually have to go calculate that. So I'm going to save us the time. I'm going to bring Desmos in here. Let me fix it. See, I had it originally like that, so let me fix it. There we go. I'm going to integrate from 0 to 1 the square root of x minus x dx. I did something wrong here. I think I have to go. There we go. Okay, so our answer as a decimal is 0.1666666. Okay, that's the area of the region. Any questions? Okay, so that's part A. If I do part B, I should get the same answer, but we're going to do it with horizontal rectangles. So I'm going to draw that picture again. I'm going to go a little faster with my picture. I don't have to be super accurate with this. So if I'm going to do horizontal rectangles this time, then I cannot be working with these as functions of x. I have to see if I can represent these as functions of y. That means I have to take the original equations, and instead of solving them for y, or having them solve for y, I need to solve them both for x. So that means I need on the left one to square both sides. And then on the right one, well, it's already solved for x. X is equal to y. So if I label these now, this green one is the one that's x equals y, and the blue one is the x equals y squared. Now it's only the top half of it, but we can still look at that as the function y squared. So now we have a right and a left, right? We have a right and a left. We also need to figure out our limits of integration, which will go from 0 up to where they hit up here. So we're looking at the y coordinates for the limits of integration, but that also turns out to be 0 to 1. Just for this particular example, that's what it is. So my integral will be the integral from 0 to 1, and then I'm going to do right minus left. So the right, what's the right one?
X equals y.
Okay, so what am I going to put in here? For the right, what am I going to put?
Would just be y.
So one thing to remember is when you're doing your horizontal rectangles, remember we're going to have dy at the end. That means that everything inside that integral has to be in terms of y. So y goes there, and then minus the one on the left, which is the x equals y squared. So I put y squared here. Now notice that these two integrals are different, right? These are different integrals. So the antiderivative of this is different than the antiderivative of this, but it's going to give us the same answer. So I'm going to go back to Desmos. I'm going to integrate from 0 to 1. I'm going to integrate y minus y squared dy. And I get 0.1666666. So I get the same result. All right. Are there any questions on that? Now, under normal circumstances, you don't have a choice. Like you have to do vertical rectangles because they're both functions of x. You can't look at them as functions of y, or the other way around. They're both functions of y. You can't look at them as functions of x. But whenever we're given a function or a curve that can be looked at from both perspectives, you can do it either way. And I just gave you that example so that we could do it both ways. All right, let's look at part C. So now we get to the volume, right? So this is now a completely different concept because we're talking about volume. And we will still work with the same region, but now I'm going to be taking a little bit of extra time to be careful with how I draw things. And this again is just because of where we're about to go with this. It's best that we start to get used to a certain kind of approach. So I imagine here again, I have a rectangle in here. My axis of rotation is the x-axis. I'm going to do that in orange just to remind us that's what we're revolving around. So when we rotate that around the whole region, we get some solid and we're trying to find the volume. So what I do, and I recommend you do, is to the right, draw the x-axis. So what I'm doing is I'm just taking the x-axis and drawing a little section of it over here. I'm taking my rectangle and just kind of moving it over to the side. And then I also like to label like the top curve. See, I have colors, so it's easier for me to label these. I have the blue one on top and green one on bottom. But if you wanted to, you could actually label those by just saying, okay, that one is the square root of x, right? And this one right here is just x. So I've labeled that. Now, very important, the axis of rotation. So I'm gonna do that in orange. My axis of rotation is actually my x-axis, right? It's in the same position as my x-axis. So I'm gonna draw my little circle here. And now all I really need to know, right? If you look at the formula for this, I'll write the formula down. It's pi integral a to b. It's r out squared minus r in squared dx. So I just need to figure out what the outer radius is and what the inner radius is. So imagine you're a person standing on the axis of rotation. So see that little purple dot? Imagine we're looking from the top straight down, okay? And we see this person's head. And they're looking out at this rectangle that's laying on the ground out in front of them. And they have a measuring tape, and they're trying to figure out what is the distance from them, the axis of rotation, all the way to the outer edge of the rectangle. That's the edge of the rectangle that's furthest away from them. And for us, that's just the square root of x, right? So that's r out for us in this problem is just the square root of x, because that's the blue curve, right? That's the distance from the x-axis to the blue curve. That's square root of x. And then the inner one, same thing. Distance from there to there is just x. So there's nothing new here from last time, but are there any questions? Okay, so my integral should be pi. What are my limits of integration going to be?
Square root of x squared minus x squared.
I'm talking about the numbers here.
Would it still be 0 and 1?
Yeah, so we're still imagining that we're sliding a rectangle through, right? We're still doing that, but it's that we're not finding the areas of those rectangles. We're finding the volumes of the washers that are created when we slide the rectangle. So we're still going to be going from 0 to 1. We're still sliding that rectangle through. Does that make sense? And then the outer radius, which is the square root of x, but I have to square that, minus the inner radius, which is just x, but I have to square that, and then dx, which turns out to be pi integral 0 to 1. Let's see, when we square the square root of x, we get x, and when we square x, we get x squared dx. Whatever that is, right? Let's go ahead and get it since I have it right here. This will be the integral from 0 to 1. I'm going to put pi here. It was the outer radius squared, which turned out to be x, and then minus the inner radius squared, which was x squared, and then dx. So the volume of that solid would be 0.523598. Now, like, we don't know if that's, cubic inches, cubic feet. It's unitless at this point, but it's the numerical value of that volume. Is everyone okay with this? Now, what if I change things and I say, you know what? Let's wrap this around the y-axis. What if you take that same region? So I'm going to add a part D to this. What if we try and wrap this around the y-axis? Oops, I went to the wrong place. Volume of solid about the y-axis. So we have that same region. Now we're going to wrap around the y-axis. So let me ask you first, do you think we get the same volume? Let's do a poll. Yes, you think it'll be the same? No, you think it'll be different? Okay, so we're about 50-50 on the yes and no. So let's just go figure it out. So first of all, please notice that if we do vertical rectangles, it won't work, because vertical rectangles are, when we wrap around the x-axis, that's how we create our washers, right? By wrapping those vertical rectangles around the x-axis. We can't do that because we want to wrap around the y-axis. So which type of rectangle should we use? Horizontal, good. So we're just going to put a horizontal rectangle here. It's the same principle. I have my axis of rotation as the y-axis. I'm going to put an orange there. So what's happening is when we wrap this thing, when we wrap that that rectangle around, we get a washer that looks more like a washer that's just lying on a table, right? That's what that thing wrapped around would be. The difference is that we're going to move our rectangle up and down, which is going to create a bunch of washers up and down. So we've got that. We also have learned from previous parts of this problem that this is 1 up here and this is 0 down here. So we know that our y is going to vary between 0 and 1. Let me do what I did before. You know how I told you to draw the picture off to the side? Well, because this is wrapped around the y-axis, here's what I'm doing. I'm going to draw my y-axis here. I'm going to draw my rectangle here. I'm going to notice that the green one is here and that the blue one is here. My axis of rotation is also the y-axis. So the formula should just follow from before. It should be pi integral. This time I'm going to go c to d. I'm using c and d because we're going up and down instead of left and right. And then it should be the same. It should be the outer radius squared minus the inner radius squared. But what's different at the end here?
dy.
dy, yeah. So dy is the thickness of the washer. Just like when we were doing vertical washers, the dx was how thick each washer was. Well, since we're going up and down, dy is the thickness of the washer. Okay, so R out. So I imagine, again, that I'm standing here on the axis of rotation. There's my purple head right there. And I'm trying to measure the distance from there to the outer edge of the rectangle, right? And that happens to just be the green one, right? So the R out should be what for us?
Y.
Y, right? So it's not X because everything's turned sideways now, right? We're doing horizontal stuff. So we're going to do everything in terms of Y. So this is going to be Y. And then the inner radius is the blue one. And for us, that's what?
Y squared.
Y squared. So I'm using stuff that we've already learned in this problem, right? If the problem was presented this like out of the box like this and we hadn't done parts A, B, and C, then you might have to do some work here, right? But because we already know this, I'm just kind of moving with this problem. All right, I think that's everything we need. So this should be pi integral 0 to 1, because we know that the upper limit there is 1. The outer radius squared, so y squared, right? Y, we take the y and then square it. And then the inner radius, which is y squared, squared dy. So this is pi integral 0 to 1 of y squared minus y to the 4th, which of course we could do that by hand, but I'm just going to use the computer again. We had 58% of you said that you thought it would be the same, and 42% said no. So we're about to find out. So integral 0 to 1 pi, and then it was y squared minus y to the 4th, oops, dy, boom, 0.481, sorry, 0.41887. Okay, so the reason is because it's a different shape. It's a completely different shape. Let me give you another example that I think would be easier for you to see that in general, you won't get the same shape. So like, we'll make it simple. Let's say that we took this region right here, just this little triangle right there. Let's say we wrap that around, or you know what? Yeah, I'll make it a little bit better. I'll move it here. Let's say we take that triangle right there, that region in here, and we wrap it around the x-axis. If we do that, we're going to get a cone, right? Our axis of rotation is right through the center of this thing. Do you all see that? Wrap that triangle around the x-axis, you get this cone. Now, if you wrap it around the y-axis, you don't get a cone, right? You get something that would look more like this. It would have straight walls on the end like this. And then on the inside, it would taper down like that. I hope that kind of, I don't know, that's about as good as I'm going to be able to get it, right? Do y'all kind of see that? That would be this thing wrapped around the y-axis. These are completely different objects, and so they'll have different volumes. So in general, wrapping around the x and the y give you different volumes. Okay, good. Everyone doing okay with this so far? Any questions? So what we did is we went around the y-axis, and I really didn't present you with any new formulas. It was more of an idea, right? It's the same formula, but used from a different perspective. All right, so now I'm going to add a part E to this. So I want the volume again, but I want it wrapped around this. So whenever we say we want it to go, around the x-axis or around the y-axis, we use the word about. So rotate it about. So I could say about the x-axis or about the y-axis, or I could say this, about y equals -3. Okay. So this is different. So let's see. I'm going to draw my picture. There's my region. I want to wrap that thing about y equals -3. So what is y equals -3? What is that? It's just a horizontal line. That's all it is. Okay. So if I go down 3, 1, 2, 3 to -3, here's my axis of rotation. Now I usually do my axis of rotation dotted. I've been doing it solid because it's been right on top of the x-axis. But when it's not on the x-axis or y-axis, I like to draw a dotted axis of rotation. And I'm still going to put this here like that. Okay, everyone understand? Does everyone agree that we're going to get a different volume than just wrapping it around the x-axis, because we have a much bigger radius now because our axis of rotation is really far away from us. Yes? So I'm going to do the same thing. I have a rectangle over here. I'm going to move my rectangle over to the side. I'm going to draw my x-axis. Oops, that's meant to be black there. I'm going to draw my x-axis. I'm going to draw my axis of rotation down here. I am going to label the top edge here as, oh, that's blue, never mind. The blue curve is on top, the green curve is on the bottom. Now, you're standing on your axis of rotation. There's your little purple head, and you're looking out at this rectangle. And you're trying to find the outer radius, which would be the distance from you to the outer edge of the rectangle. What is it?
That'd be the square root of x minus 3.
Okay, square root of x minus 3. Let's think about that. So what Ross is thinking is the distance from the outer edge to the x-axis, right? Just that part, we know that that is the square root of x. And then the rest of the way, okay, so the rest of the distance from here down to here, you're using -3, right? But Ross, think about this as like a measuring tape. Okay, it's a distance. So we want to look at everything as being positive. So even though the line is -3, the distance is +3, isn't it? And so that's what we want to represent that bottom piece as. We want to look at this distance from here to here as being 3. And then the distance, the rest of the way, was the square root of x, which means my outer radius would be not square root of x minus 3, but square root of x plus 3. See, it's a distance. Does everyone understand that? Okay, so using that same principle, the distance, the inner radius is the distance from the inner edge of the rectangle all the way to the axis of rotation. That would be what?
X plus 3.
X plus 3. So the x part is the distance from the bottom edge just to the x-axis. That's x, and then the rest of the distance is 3. And so now if we set up the integral, everything else will be the same. We're going to go pi, integral is still going to go from 0 to 1. But now we have the outer radius, square root of x plus 3, that quantity squared, minus the inner radius, x plus 3, that quantity squared dx. And yes, you would have to FOIL all that out, right? You would have to like expand everything, collect like terms, find the antiderivatives, do your fundamental theorem of calculus, and you would get a volume. Now, I'm not going to do that. I'm just going to leave that. I'm not even going to go over and get the answer from the computer. On your next exam, I'm going to have you calculate some of these integrals all the way to give me an answer. It'll probably be the area problems that I give you, that I'll ask you for the actual numerical answer. But then we'll get to a point where I will no longer ask you for the answer, I'll ask you for the setup of the integral. So that right there that I have boxed is what I'm going to look for. In fact, I have an old exam here that I can show you where what I did, let me make this a little bigger. Look at number 3. Well, look at number 2. Find the area of the region bounded by these curves. Your graph should be clearly labeled. Write your answer as a decimal. So I wanted that area, you know, take it all the way. And then the next one was set up these integrals, but do not evaluate them, which give the volume of the solid form by revolving the region bounded by. So I gave the students the curves to look at that allowed them to sketch the region. And then I had them rotate it around the x-axis, the y-axis, y equals -3, y equals 4, x equals 5, and x equals 3. So that's 6 integrals that had to be set up but not evaluated. So the whole key to this, at this point, the key is, can you translate the problem into the mathematical integral? And then, yeah, of course, we could get that answer if we needed to. All right, so let's try the next problem. I'm going to add a new one, part F. Now, let me kind of give you a hint, and if you haven't picked up on this yet, on what I'm trying to do here. We have this region, and what I'm going to give you examples of here is, first, how to rotate it around the x-axis. We already know how to do that. We know how to rotate it around the y-axis. We did that. Then we just rotated around a line that was below the region, right? The next one's going to be a line above the region. Then we're going to do a line over here to the left of the region, and then we're going to do a line over here to the right of the region. Okay, so that means you have basically covered all the different scenarios as to where your axis of rotation could be. A couple of my students in my other class asked me, do we ever rotate the region around like a line that has a slope that's not horizontal or vertical? And the answer is no, we don't in this class. In fact, I can't remember a class that I ever took that we had to do that, but it can be done. You have to do a rotation of the whole coordinate plane. So it requires a matrices, a linear transformation. When you take linear algebra, they talk about linear transformations, and you have a certain matrix that'll rotate your entire two-dimensional space. So you would have to basically like rotate your space and then go back and do this, but we're not doing that. And then also, yeah, no, that's good. Okay, let's do part F. Any questions while I'm writing out part F? We want the volume. If we rotate about y equals 4. So if I'm going to give you problems like this on the test, can you see how important it is to get your region correct to start, right? I mean, like if you get your region wrong, like everything's going to be off. And then I'm going to be all grumpy because I have to figure out whether or not you did it right based on your incorrect region. So you want to make sure you take time to get your region correctly drawn. Okay, there's my graphs. My axis of rotation's up here at 4. Oh, I remember what I was going to say. Your axis of rotation will never go through the middle of your region. Okay. It gets weird when you do that. If you just think about what happens if you rotate, you get like it doubles your volume. It's strange. Okay. So there's our axis of rotation up there at 4. I've got my rectangle. And I'm going to draw my little rectangle over here to the side. I'm going to draw my x-axis. You might be wondering, why are you drawing your x-axis? Well, just do it. You'll see. Draw my axis of rotation up here. I know that the blue curve is the top edge. I know that the green curve is the bottom edge. Now, I am standing up here, right? So the outer radius is the distance from me to the outer edge of the rectangle, which is no longer the blue curve, right? It's here to here, right? To that edge, to the green edge is the outer edge relative to the person, you know, standing on the axis of rotation. So everyone see that? That's your R out. And your R in is from here to here. That's your R in. And so what we need to figure out is what are those, like how long are those? How, you know, what's R out and what's R in? So does someone see how to get it? Someone tell me what R out is and maybe kind of explain why it's that.
I got x plus 4.
X plus 4. Okay, so you're on the right track because you're using X, which is the bottom curve.
Mhm.
But okay, so X is this distance, right? This distance from here to here is X. Do you agree?
Sure.
If I take that and I add 4 to it, won't I be like way up here? I want this distance from here to here.
Would it be 4 minus x?
4 minus X. Who said that?
Me.
Okay, so Ross. So let's think about what Ross is saying. 4. Where is 4 on this graph? 4 is the distance from here to here, always, isn't it? Isn't that full distance from the axis rotation down to the x-axis? That's always 4. And so if I take that 4 and I subtract from it this x, I will have that gray area, that gray length, won't I? So that's exactly it. It's the outer radius is 4, take away the x. It's very important that everyone sees that.
Four minus root x.
Here's one way you might be able to look at this. that might help with that. I'm going to zoom in over here. Okay, so imagine that you had a rectangle right now that was right there at the origin. Now it's this little infinitesimal rectangle right there. Okay. How far away would that outer edge of the rectangle be? If you're right there at 0, okay, so if our x value is 0, right? How far away is the outer edge? 4, right? 4 units away. Okay, so now say we're at 1. Say we're at 1, x is equal to 1. Right there. Well, we know this value is 1 right here. Now it's not drawn to scale, but what would that distance have to be then? If we know the distance from here to here is 1, that would have to be what? 3, right? Because it adds up to be 4. So we know this is 3. And if you look at the formula we came up with, 4 minus x, this formula works. If you plug in 0, you get 4, which makes sense. If you plug in 1, you get 3, which makes sense. If that helped, good. If it didn't, sorry. Okay, what about Rn? Same principle, right? What do we have?
4 minus root x.
4 minus root x. So we know the distance from here to here is root x. And so Rn should be the whole 4, take away the root x. And that's it. We set up our integral. Pi integral 0 to 1, outer radius squared minus inner radius squared dx. You know what I like about these problems? From my perspective, they're so easy to grade. Like these problems are so easy to grade compared to like trying to figure out what the hell you're doing with an integral, right? Where you're doing all these weird partial fractions, long division, trying to find mistakes. These, I just look at the integral. Like if that integral is right, then yeah, you know what you're doing, right? It's hard to come up with an integral, just like randomly get it right. I mean, you have to think about the position of things. Okay. I had a student last time trying to come up with like a more of like a cookie cutter approach. They were like, okay, so what you're saying is if the line is below, then it's just take that number and make it positive and add it, add it to the function or something like, and they kept on trying to find like these little, I guess, shortcut ways. And I just told them, don't, just draw the picture. And here's why. Like, I could always come up with an example that would throw you off. Like I could always do something like, let's just say you had a region, just to be quick here. Let's say your region was this right here. Okay. Let's say the one on top is F and the one on the bottom is G. Okay. So we got these curves coming through here, whatever. And let's say I ask you to rotate it around this line right there. Y equals, let's say 1. Now that is below the curve, right? It is below the curve. But if you're going to use something like, well, you know, oh, if it's below, then I just take that number and add it to the function. It won't work because look what happens. If I draw a rectangle here, move it to the side, put my x-axis, put my axis of rotation here, then I'm standing on the axis of rotation. And so the outer radius is here. The inner radius is here. And this distance is the f function. That distance is the g function. Do y'all see that? And so r out would be what? What would the distance from here to here be?
It'd be f minus 1.
F minus 1. Because the distance from here to here is 1, right? But the distance all the way from here to here is f. So this purple distance is f minus 1, and this one would be g minus 1. So it's very dangerous to try and just get into a thing where you're like, you know what I'm saying? Like trying to get a shortcut. If you draw the picture, you'll get it. As long as you understand, as long as you understand how this is all working, you'll be safe. It's much safer than trying to do like a cookie cutter way of doing every problem. I hope that makes sense. I always tell my classes that if there was a shortcut that I could show you to do a specific problem that worked every time, I would show it to you. Like I would give you that shortcut. That would be the way I show you to do it. But if it doesn't work for every case, I'm not willing to give you a shortcut, right? All right, where are we? We're done with this? Okay, now we're gonna move part F, part G. Let's rotate about x equals -10. So I'm going to draw a picture. Getting tired of drawing this. How about you?
Same.
No. X equals -10. Why did I do that to myself? It's all right. I'll just put -10 right there. X equals -10 is a vertical line. We're rotating around here. So how would you venture that we go about this?
Is that a vertical or rectangle? Rectangles use horizontal.
Yeah, we could use horizontal here, right? Now, if we do horizontal, right, then we need to draw our picture below this. So let me zoom out. Okay, below this, I would have my rectangle. I know I have the green one on the right, the blue one on the left. I have my y-axis here. I have my axis of rotation here. I'm standing on the axis of rotation. I'm looking out towards the rectangle. All the way out, that's R out. And R in is that distance there. So R out. Someone want to tell me what R out would be? R in?
Y plus 10.
What was that? I didn't hear.
I said y plus 10.
Y plus 10. Okay, so good. So Alex is saying, okay, look, the green curve right here is y, right? Remember, we have to switch everything to functions of y now. So that's y. The inner one there, that's y squared. And so Alex is saying, all right, the distance from the y-axis to that outer edge, that's y, but you have to add the additional 10 that's there. So 10 plus y. Similarly, the inner radius should be 10 plus y squared for the same exact argument, right? And that's it. You got it. Pi integral 0 to 1. Now 0 to 1 is because C and D now, right? We're talking about the one up here, not 0 to 1 on the X. And then we have outer radius squared, 10 plus y, that squared minus the inner radius squared, 10 plus y squared, and then dy. Also, don't forget you have to square these, like FOIL them, right? Don't square each one, right? I mean, that's obvious, but sometimes when we get so far down the road in math, we start to like make mistakes that we know we shouldn't be doing, but it happens. All right. Okay, that's it. That's the integral. Now, I think to save time is what I'm gonna do is I'm just gonna copy this page. Okay, and then I'm just going to change some stuff here. E, F, G, H. Let's go around x equals positive 10 this time. Okay, so that's going to change, all that's going to be gone. Okay, so positive 10's over here. I still draw my y-axis. I still draw my rectangle. It's still the blue on the left, still the green on the right. I have my axis of rotation. Why don't you all see if you can get that one? I'll give you a minute. I want to look something up real quick. All right, how'd y'all do there? Did I give y'all enough time? I'm sorry, I meant to end that poll a long time ago. I don't know if that's on your screen bothering you, but someone want to tell me what they got?
I got pi from 0 to 1 of 10 minus y squared
Good,
minus 10 minus y.
good, perfect. That's right. So using the fact that the distance from here to here is y squared, the distance from here to here is y, and that the total distance from the y-axis to here is 10, then the outer radius is a distance from here to here, which is there, and then distance from here to here is the inner radius. Okay. How do y'all feel about this? I mean, does it at least make sense? I mean, you'll have to go and do your own examples and see how things go, but y'all are okay? Okay, so I wanted to show you the book real quick. Because as you might imagine, this would be a hard thing to explain in a book, wouldn't it? So the book, this is, you know how on the side I said draw your little thing on the side, the rectangle, and find the distances. This is the book's version of that. Okay, just so you see the way they're doing it. All right, they're using a three-dimensional picture instead of what we're doing. We're using rectangle. So what I drew, let me zoom in on this. Maybe, well, I may not be able to. What I did is I drew the rectangle right here. And then we were talking about, oh, the distance from here to here is X, distance from here to here is X squared. So this is where I put my little curve on top and bottom. And then this is their axis of rotation up here. And then they're doing this is their R in, and this is their R out. I guess the reason I'm showing you this is because you're not going to find in any textbook anybody talking about R in and R out. That's just the way it's always made sense to me. So that's the way I'm showing it to you. All right. Let's see. I haven't looked to see what else they do here. Oh, they do R in and out. Hey, I didn't know that. Wow. I take that back. I don't remember ever seeing that. Interesting. Maybe I got it from there. I don't even remember that I got it from there, but I didn't use this textbook when I learned it. So interesting. Okay. Time for a new problem. Time to throw a wrench into it. So what I'd like for us to do is a brand new problem. I'd like for us to look at, find the volume. If region bounded by y equals 4 minus x squared x equals 0, y equals 0 in the first quadrant is rotated. Ah, shit. Sorry, I'll fix it. Rotated about the y-axis. I need to fix something, sorry. I apologize for cussing also. Sorry if I've offended any of you. Okay, hold on. I want this function to do something else. Hold on. Make it, I want to change this function. Just change all this. Let's just get rid of all this. Hold on. Let me just think what I want it to do. Okay. So how about x squared minus 2, or sorry, x squared minus 2x is what I meant to say. X squared minus 2x, y equals 0 in first quadrant. Well, I already have that there. No more. All right, let's draw a picture. Yes. Now this picture is a parabola, right? And I keep messing myself up. I apologize. One more fix. One more fix. I promise. I'll put it in red. Make that a minus and a plus. Minus and a plus. I want this thing opening down, not up. That should get it. Yeah. All right, so there we go. We want y equals negative x squared plus 2x, y equals 0 in the first quadrant. So I don't know, how would you graph that? Would you just go to a calculator? I mean, I don't know. It's a parabola, right? It opens down. We could also find the x-intercepts if we wanted to, right? If I wanted the x-intercepts, I could set it equal to 0. I could factor an x out. And I'd have two x-intercepts at 0 and at 2. So 0, let's say this is 1, and let's say this is 2. So I know I have those two x-intercepts, and I know it opens down. So the parabola's got to look like this. I don't know how high it goes, but there we go. Now your graphing calculator would have gotten you that already, right? So I want the region bounded by that, y equals 0, which is the x-axis, right? In the first quadrant, so this right here. This is my region. And I want that rotated, I want to find the volume if we rotate that around the y-axis. So our axis of rotation is here. Got it? Understand? Any questions? Does anybody see the problem, the issue, the dilemma?
We can't use horizontal rectangle.
Can't use horizontal rectangles because if you draw a horizontal rectangle, then what you wind up having is the right curve and left curves are the same curve. And that's because this blue curve is not a function of y, it is a function of x. And there's no way to solve for x here unless you take a square root. And if you take a square root, you're going to have plus or minus, so you'll have two functions, not just one. So we have a problem, right? This is a major dilemma. And there's no easy fix for it. So what we have to do is we have to rethink everything, okay? We have to rethink it all. And when I say rethink it all, I mean we have to go back. We have to go back to, hold on. We have to go back to this. Remember when we were talking about the volume of a washer and came up with a formula for it? We have to consider a new shape, okay? There's a new shape I want us to all think about, and that is what's called a cylindrical shell. This shape right here, all right? This shape is the shape that we would get if we used a vertical rectangle and wrapped it around the y-axis, right? It would not be a washer anymore. It would be this shell. Do y'all agree? Imagine that being wrapped around the y-axis, then you would get something that looks like this. And so if we could figure out a formula for the volume of this, then what we could do is we could move our rectangles through the region left to right from A to B, keeping all of our rectangles vertical, and add up all these shells. So we're really kind of trying to imagine this. Hold on, I have it. Where is it? I think it's this one. Yeah. Oh, no, that's not it. I have to go find it in my, give me a moment to find it real quick. I've got all these in a folder. There it is. Oh, shit. Okay, here we go. So the idea is that we have these rectangles. Can you all see that okay? Not anymore, huh? Get over here. So it's like we have that curve, right? And we're going to have all these rectangles. This thing is really acting buggy. Let me reevaluate everything. Okay. Okay, so we have our curve in two-dimensional space. We do all these rectangles in here, and we imagine that if we wrap them around the y-axis instead of the x, then as they go around, they create all these cylinders, right? All these shells. Now, it comes all the way around, okay? I stopped halfway so you could see it. If we were to somehow be able to put all those together and have like an infinite number of these in here, then what you would get is the actual solid. Now that's solid. It's hollow in the diagram, but imagine that it's solid, right? So you get the actual curvy looking, it almost looks like a bundt cake, right? This example almost looks like a bundt cake. That's what you would get if you had an infinite number of rectangles in there. But the main thing to take away from this is that you have this new concept of a shell as opposed to a washer. And I think you could argue that they're the same thing, right? Like if I turn a washer this way, then you could argue that that's a shell, right? You could maybe, and they're both basically the same thing. But as you'll see, the formula for this is going to be very different than the formula for this one. So let's see if we can't come up with a formula. So I need to start a new page. We'll get back to that example. I need to start a new page to talk about this new idea of using shells instead of washers. So we start with the curve, or a region, sorry. Let's say we have a region, okay, from A to B. And the idea here is that we can only do vertical rectangles. So we're forced to do vertical rectangles. These are functions of X. There's no way to get them as functions of Y. So if we're in this scenario and we wrap that around, right? If we take that and wrap that around, we get this. So we're wrapping it around the Y-axis. If we do that, we get this shell. Now, to consider the volume of this, here's what I'd like for you to do. I'd like for you to come in here with a pair of scissors, and I'd like for you to cut this shell, cut it open, okay? So imagine cutting that shell and laying it out flat. So you have to imagine that this thing is, what's the word I'm looking for? Malleable? Is malleable the right word for that? Malleable? Yeah. You can move it around, it's flexible. Okay, so if I lay that out flat, do y'all agree that I'm gonna get this really, really long, skinny little strip like this, right? That's what would happen if I laid it out. Okay, well, if that's just a box, that's all that is a box. And the volume of a box is easy to find. It's just length times width times height. So let's talk about the things we know right off the bat. How about this little thickness? How thick is that side right there, that little piece? Where does it come from?
Is that R out minus RN?
This thing wrapped around creates this shell, right? So it's that rectangle getting wrapped around. The thickness of that should be the thickness of the rectangle, shouldn't it? And the thickness of the rectangle is just dx, right? That's just dx. Let's go after the next thing. Do we know how tall this is? Well, that's just the height of the rectangle, isn't it? Which is the
Top minus bottom.
Top minus bottom. Okay, so this is just the top minus the bottom. The trickiest part is to figure out how long it is. All right. So to help you see this, I brought a visual aid with me today. Just a piece of paper. So this is our shell, right? This is our shell. And we cut it and we opened it up, right? And that's what we have, but it's got a little bit of thickness to it. That's the dx, right? So my question is, how long is this, right? We know that the height is top minus bottom. Thickness is dx. This length should also be the what of this?
Circumference.
Circumference, right? It should be the circumference of that circle, which means that the circumference should be 2 pi times the radius. 2 pi r is circumference, which means we need to know the radius of this, right? The radius. Now go back up to where this came from. This rectangle got wrapped around the y-axis, didn't it? So the distance from the y-axis to that rectangle is the radius. And what did I say that was earlier? Very beginning of class. The rectangle slides across, right, from A to B. And if you were to stop that rectangle at any point in time, the distance from the rectangle to the y-axis is always going to be
X.
X. Okay? So for us here, this distance, R, is actually X. And so the volume of that thing right there, the volume of it should be length times width times height. So it's 2 pi x times the top minus the bottom. I have to put that in parentheses because I have to subtract that before I can multiply, and then times dx. That's the volume of one of them. You want the volume of all of them, right? Added up together. You want all the rectangles to move across. So to get the volume of this, the total volume will be 2 pi, that's a constant I can pull out, right? That 2 pi can come out. Integral, I'm going to go from A to B because x is going to vary from A to B. It'll be x top minus bottom dx. I'm going to put this here, box it because it's real important, but I'm going to put question marks next to it because this is actually not the final version that I'm going to give you. All right, the final version I'm going to give you is one that I'll give you in just a moment. All right, you ready? Let's go back to the example that we just did, that we were working on. We got stuck. So we have this region. We have to wrap it around the y-axis. And we realize we can't do horizontal rectangles. We have to stick with vertical rectangles. And because we have to stick with vertical rectangles, we know we have to do shells. Okay, so here's a thing that'll help you remember when to use shells and when not to. If your rectangle is perpendicular to your axis of rotation, okay, you're going to be using washers. If your rectangle is parallel to your axis of rotation, you're using shells. So in this case, our rectangle is vertical, our rotation axis is vertical, and so we need to use shells to do this, right? All right, so here it is. I mean, there's not a lot that we have to do. It's just we have to recognize what the top and bottom are, right? So our top here is just negative x squared plus 2x. The bottom curve is what? Well, just 0, right? We know that the distance from the axis of rotation over to this, we know that that's x. I think we know our limits of integration. We start at 0, we end at 2. There's really nothing else more, right? 2 pi integral 0 to 2 x top minus bottom. I'm going to put 0 here even though we don't need it. Dx. So we could clean that up, but understand? I'm going to give you one now. Same exact region, okay? The same region. Same one. But don't go across the y-axis. I want you to rotate that around x equals -2. Be careful. All right? I'm going to give you let's say 5 minutes. See what you can come up with. If you do finish that one, then try it around x equals 5. So basically, I've given you another axis of rotation to the left and another one to the right. I want to see if you can come up with something there. Do y'all want breakout rooms or you just want to work on your own? Do y'all care? I'm going to do breakout rooms. And maybe we'll make it more like 10 minutes. Maybe not. I don't know. Here's breakout rooms for you. We really don't have 10 minutes, but it'll be fun. Here you go. Okay. So I'm not sure, I didn't check in on the groups, but hopefully you got your pictures set up something like this. On the first one, your axis of rotation is x equals -2. You still can't use horizontal rectangle, so you have to stick with vertical. So you're gonna use shells. You know the formula is 2 pi a to b, you know it's top minus bottom dx. The question was this radius, this x. That's the distance from the axis of rotation. Did y'all get the message I sent y'all? I sent a text and I sent a message to everyone. Okay, some of you got it, some of you didn't. But in the first example, I said that is x, right? But in general, it's not, because here, x is the distance from the y-axis to the rectangle, but it's not the distance from the axis of rotation to the rectangle. And that's what we need. So what would this be here for us in this problem?
2 plus x.
2 plus x. Okay, so what I do is I start to call this distance from the axis of rotation to the rectangle, I start to call it r sub x. It's the radius, but it depends on x. Like it should have an x in there, but it might just be x, it might be some little function of x. Now look at the second one. We know that our axis of rotation is over here on the side. So when we wrap these things around, they're going to go like that and create these cylinders like this. But our radius then is this distance from here to here, which I have highlighted, or I have in the black there. Point an arrow at it, that one. So what we need to do is figure out what's the distance from the axis of rotation to the rectangle. Well, just like kind of we did with the washer method, we know the distance from the y-axis to our axis of rotation is 5, that's fixed. We know the distance from the y-axis to the rectangle is x. So what should this be for this one?
5 minus x.
5 minus x. 5 take away x. So if I were to redo that formula, the one that I put a box around, put question marks on, if I were to redo it, I would write it this way: 2 pi integral a to b r sub x top minus bottom dx, where r sub x is the distance from axis of rotation to the rectangle. And just remember that x
I don't know.
is
What
the
time?
distance.
But then we have to go over there and get the.
No, I mean, we have time from the third.
X is the distance from the y-axis to the rectangle. So x itself will always be the distance. That's always the distance from the y-axis to the rectangle. But r sub x needs to be the distance from the axis of rotation to the rectangle. There's a difference between those, unless you are rotating around the y-axis. Okay. That's a majority of 7.2, along with 7.3 is not in your homework. The section 7.3 is called shells. Okay, so I've just blended shells into 7.2. So when you do your homework for 7.2, you are free to do any method you want. All right. Like, for example, if we go back up to this problem right here. Where was it? Right here. Remember this problem, part D of this problem? We wanted to find the volume of this solid about the y-axis. This was square root of x, and this was x, right? This was the first problem we started with. Remember we did that and we set up the integral here? We never got the answer. But what we did when we did this problem is we used horizontal rectangles. And the reason we did that is because we could write these as functions of y. What I'm telling you now is that you could do this problem without using shells, because you could do a vertical rectangle in here. And your distance from the axis of rotation to your rectangle is X. And you know your top and bottom, right? That's your top, that's your bottom. So this should just be, I'm gonna write it down here. This should just be 2 pi integral 0 to 1, because we are starting at 0 and ending at 1. And then it should be X, which is the radius. And then it should be the top function, square root of X, minus the bottom function, X, dx. And I claim that these two integrals give you the same answer. We shall check. Does anyone have a question on this though? This was using shells. This was doing washers. Which again, you can't always do it. You can't always do both, but you're free in your homework and on your exam to use any method you want. I'm gonna check that. I'm gonna see if it's right. Let me go to Desmos. I'm gonna put this right here. So we're gonna do the integral 0 to 1. Let's do the washers one first. It was pi. It was y squared minus y to the 4th. Maybe we did find this answer. I don't know, did we? Yeah, we did do that, didn't we? And then the other one is integral 0 to 1, 2 pi times x times square root of x minus x dx. Oh, same answer. Okay, same answer. All right, so we've got some very powerful stuff on board now. We can do a lot with this. We can rotate pretty much anything around any axis and or any line and be able to come up with a numerical value. All right, it's 12:33. I just want to at least talk about the last thing. There's one more thing in 7.2. Just want to at least talk about it. We'll finish it up next time. So I've tried to kind of push this into your brains since we started the whole idea of the integral, that the integral just adds things up, right? Adds up an infinite number of things. What's in here really depends on the geometry of the problem. I mean, it could be areas of rectangles, it could be volumes of washers, it could be volumes of shells. It can be anything though. There's no restriction on, what that can be. So I want you to think about this physical problem, and then we're going to somehow use an integral to solve it. So I want you to consider a solid ball that's been cut in half, right? So I have this solid ball that's cut in half, all right? So it's a golf ball, an orange, whatever, we've cut it in half, there it is, right? So would you agree that the base, and let me give it a radius. Let me give this thing a radius of, let's say 2. Would you agree that the base of this solid is a circle, radius 2? Would y'all agree with that? So
Yes,
if
sir.
I were to be looking from the top down and I put my ball right like this, that's not a very good circle, but you agree that this is what the footprint of that ball, of that object would be, yes, on the ground. Now, do you agree with this also, that if I were to, so right now we're looking straight down on this ball, right? I mean, it's actually a ball, okay, but that's the footprint. Okay, so imagine now that I took a knife and I cut that knife. I could cut anywhere on this ball, right? I could cut just straight down, but I want to cut a particular way. I want my knife to be perpendicular to the x-axis. So I'm gonna take a knife and I'm gonna cut it right there. So I cut it and I take this side and I just throw it away, okay? And we come in from the side and we look at it from the side. What would we see from the side? In other words, we cut it. Hold on. It's gonna be a little, here, I'll do it on this one. We cut it, right? We cut it right there. So we cut it and we threw away part of it. So what would be left would look like this. Roughly speaking, yes. If we look at it from the side, what are we looking at?
A semicircle.
Semicircle, right? A semicircle. Now, if I cut it at a different place, I would still, if I looked at it from the side, would it still be a semicircle? Would it be the same size? Would not be the same size semicircle, right? It'd be smaller. So if I cut it further towards the right, it would go like this. Okay, so that's if I cut it here. If I cut it further to the edge, it would be a smaller semicircle, right? The biggest semicircle would be if I cut it right in the middle, right? But as you get closer to the edge, the semicircles get smaller. Yes? Everyone agreeing with this, understanding? Okay,
Mhm.
now. Clear your minds. And let's act like we didn't just do that, all right? I'm going to describe for you a solid, all right? Here's what I'm gonna tell you about the solid. The base of the solid is a circle of radius 2. But when you do cross sections, cuts into this solid that are perpendicular to the x-axis, you get equilateral triangles. Is that still a ball?
Wouldn't it be a cone?
It'd be kind of conical, kind of. Maybe it's a cone. Maybe. What if I told you that you have a solid where the base is a circle, but when you do a cross section, you get a square? Is that a ball? It's not. Okay, so let's go with that one. Let's go with that one. You have a solid. The base of it is a circle of radius 2, and cross sections perpendicular to the x-axis are squares. What's the volume of that solid? That's the question. Okay, so I only have 1 minute. I'm gonna give you a rough draft of how we're gonna do this. We say, okay, that we're given that the base is a circle, has radius of 2. We know that when we do a cross section cut like this, we get a square. So what I'm gonna do is to the side, this is the first time we're ever doing this, I'm gonna try and draw this picture in 3-dimensional space. And I'll tell you how to do that better later, next class, how to draw this 3-dimensional space. Okay, there's my circle laying on the ground. Hopefully you can see that. Here's my cut. And what I know is that the cross section, when it sticks up here, is a square, like that. If I were to cut it closer to the edge of the circle, I would have another square, but it wouldn't be as big. Can you all imagine this thing? No, if I cut it right in the middle, I'd have a square to be really big. Yeah. And I want to know the volume of this. So what we're going to do is we're going to say, all right, we're going to cut it with a knife, but we're going to imagine that we're not going to cut, we're going to cut a sliver out of this. So I'm going to give that little cut a thickness. And that means that would give this little cut over here a thickness. And so the question is, can we come up with the formula for the volume of that one little sliver? Can we find a volume for that? Okay, well, it should be just whatever this side is times this side, right? That would give you the area, and then we multiply by the thickness, which guess what? Is going to be dx, because we're going to let x go back and forth. So if we could just find this little formula for this volume of this one piece, then we could use the integral to add them all up. Does that make sense?
Yes,
Okay,
sir.
that's what we're gonna do next class. I do want to show you one thing, and then, I mean, if you have to go, go. You're not gonna hurt my feelings. But this is an animation that I wrote that will give you a better idea of what we're doing here. So we have, now this time the base of this is not a circle. I just put two parabolas together. Okay, so we have two parabolas like that. So the base of our solid is the region between two parabolas. And let's do cross sections are squares. So anywhere that I go here, my square gets bigger and it gets smaller as I get to the edge, right? All the way through this thing, that's what happens. If I were to put all of those together, right, I would get that object right there. That would be the shape that I get. So this is not a solid that we create by revolving anything around any axes, nothing like that. This is just a weird shape. And we're going to try and find the volume of something like that. If we wanted, we could do semicircles instead. That's what it would look like if it were semicircles. Rectangles. Rectangles and squares are pretty similar. That says semicircles, but this is equilateral triangle. So all of these objects are different. Like that's different than that. They're all different shapes. They should have different volumes. Okay, your homework for tonight is, and for the weekend, is to get through as much of 7.2 as you can, but you will not be able to handle 38 and 39. Those are problems with cross sections, all right? But you should be able to do through 1 through 19 odd. And I would encourage you to do more. If you get through those, try the even ones. And if you want to get real adventurous, go into 7.3, which is the section on shells, and do problems there, you know, if you just want more practice. All right, any questions? I'm gonna wrap it up for the day. Wrap it up
That'll
for
be
the
all for
week.
today, sir.
Okay, that's it. You all have a great one.
Hey, you too. Take it easy.
Thank you, sir. Have a good one.
Oh, I will send the notes out in an email right now. Okay,
Appreciate it, sir. Thank you.
Thank you.
Have a good weekend.
you too.
Have a good one.